Hello, my name is Buckelew, and this is my Lab 1 charge tapes. To introduce, I became familiar with the idea of charge and property of matter, designing experiments using household objects, making estimates and simplifying assumptions, and the amount of excess charge on everyday objects. The purpose of this lab is to do an experiment to determine approximately how much excess charge is on one piece of charge clear tape. The results, we found that the tape had a charge of negative 2.92 e to the negative 8 coulombs, which means that we had an excess of electrons on the tape. We needed a roll of clear tape, a ruler, a flat surface, and two thick books for support. To start, you create a U-tape or upper tape by pulling one end of upper tape off the base tape as seen in figure 1. Rub this upper tape against a plastic pen such that the two repel against each other. Repeat these first two steps again so that you have two negatively charged U-tapes, tape A and tape B. Place tape B on two bucks for support and lift tape A under tape B until tape B starts to move upwards in a repelling motion, as you can see in figure 2. And then measure the distance between these two tapes when they start to repel one another with a ruler. So I expected two interacting U-tapes to repel one another, whether they were both negative or positively charged. I knew that they would repel. And as expected, the two tapes did repel one another. The U-tape is attracted to the neutral object because they're somewhat oppositely charged, not completely. If the U-tape is positively charged and the plastic pen is negatively charged, then the two objects should attract. Now, if it is negatively charged, then they should repel each other. So, by making the pen negatively charged, we know that the U-tape is positively charged because the two objects were attracted to one another. Since the momentum of tape B was not changing, we can conclude that the y component of the force on tape B must have been 0. We know that tape A exerts an electric force upwards on tape B, and Earth's gravitational force exerts in a downwards direction on tape B. As you can see in my free body diagram, we have Fe and Fg, which are about the same size and magnitude, pointing in opposite directions. The length of my piece of tape was 0.204 meters. It had a mass of 2.04 e to the negative 4 kilograms. It was 0.03 meters away from tape A when it began to float, and the magnitude of both the gravitational force and electric force on tape B was 1.99 e to the negative 3 newtons, and the measured electric charge on tape B was 2.92 e to the negative 8th coulomb. Here are my calculations where I calculate the gravitational force on tape B using mass times gravity to get negative 1.99 e to the negative 3 newtons. I also find the charge on tape B to be 2.919 e to the negative 8 coulombs, which we use both of these to calculate the number of electrons on tape B to be 1.82 e to the 11 electrons. We found the number of atoms using surface area divided by the area of an atom to be 4.59 e to the 17 atoms. So we can calculate a ratio of the number of electrons to the number of atoms to be 1 to 3.97 e to the negative 7. Assumptions we made were that we can ignore air resistance, the two tapes have the same charge, and we can model the charges on each tape as a single point charge, at least in the first calculations. So I used Glowscript IDE and VPython to model my calculations and results. And here's the link. It's also attached in the bio of the video. Here I define my constants, my observed values, and my function E field, which is used to calculate the electric field using a charged particle in an observation location. Here I create the tapes, top tape and bottom tape in Glowscript. You can see they start at a 0.03 meter distance away from one another. They both have mass M and charge Q, and they're of different color. This is where I start to calculate the electric field and electric force. So we iterate through each piece of charge in top tape and each piece of charge in bottom tape to calculate the E field at the location of top tape due to bottom, and vice versa. And we create arrows for each of these to easily visualize the forces. And here you can see is my output. The white arrow is the electric force vector. The yellow arrow is the gravitational force vector. And then the green arrows are all of the sort of electric force vectors from each instance of bottom tape to top tape. And we find our magnitude of electric force to be 1.99, which is the same as our magnitude of gravitational force. So the magnitude of the charge on one piece of tape with a single point charge was 4.79 e to the negative 3 newtons, which is greater than when it was calculated as a line of charges. And this is, again, using the assumptions that we can ignore air resistance and the two tapes have the same charge. So we can conclude that the two tapes would still repel one another, as they would still have the both same sign if the signs were inversed. We can also say that the field is larger when the charge is concentrated on a single point because the collective electric field is farther away than the centralized one and also has a counteracting effect that come with different directions.